Hi everybody, welcome to the next video in our series on controls engineering in the context of Disney and attraction engineering in general. Last time we spoke about controls engineering in the broadest sense. I said it was the discipline responsible for automation, and I gave you the simple example of the thermostat in your house as a control system. You tell it what temperature you want. It measures the actual temperature in your house and then decides to kick your unit on or off to bring the temperature to where you want it to be. This is a control system in the nutshell. You have information coming in via your inputs, you have a decision being made, and then outputs being triggered to make physical equipment achieve your desired result. And our topic today is controls hardware in the context of the thermostat. The buttons or dial that you put the temperature in with, the temperature probe or thermometer that measures the actual temperature in your house, and the switch that kicks the unit on and off is your controls hardware. If you have a digital thermostat, the controls software is what reads your button pushes and displays the numbers up on the screen for you. So those are kind of your software and your hardware in that simple example. Controls hardware long predates software. Before we had computers, we were still doing industrial controls applications. We were just doing them exclusively via hardware. And the way that this was achieved was with relay cabinets, these big, massive cabinets full of relays wired up. They looked like this. Uh, ah, it's a big row after row of relay all wired together in a big rat's nest. Very difficult to troubleshoot, very difficult to maintain. It takes up a ton of space, but it was all they had at the time, so they made it work for them. Um, the way that this works is in modern situations we have control software that does all of the logic for us. And if you're familiar with any code writing at all, you know what an if statement is, right? If this and this, do this. If that or that, do this other thing. And relays are the physical manifestation of if statements. So you would take a pair of relays, and a relay is a device with a little electromagnet in it, where if you put electricity to it, it would close a contact to let electricity come across and go do something else. So what you would do is you would set up these relays in a row, and if this and this both got energized, electricity would come across out the other side and go turn on a pump or turn on a light, sound an alarm, whatever you needed it to do. If you set your relays up like this, electricity kind of comes up and stops. If either one gets powered, this or this, power comes across and out to your pump, light, alarm, whatever other device you need to control. You can also stack these into a row. So you can say, if this or this power comes down to another relay that says, if this and this get power, then it goes to. So you can build them out into layers and it gets more and more complex, but the complexity drastically increases the amount of space that takes up. Modern hardware is massively more efficient and the footprint on it is significantly smaller. To illustrate that picture that I showed you there, this guy here, that middle cabinet with that massive nest of red wires in the middle there, I can do everything that's in that cabinet with this and this, and that's it. That's how much better modern hardware is than what they were working with back then. All of that cabinet done with this, which has allowed us to do massively more complicated manufacturing processes because the footprint for the controls that you need is so much smaller. You can put 6 manufacturing lines in the space that you used to only be able to put 2 or 3 because the controls equipment that you need to run them no longer takes up entire rooms. They fit in my hand. Um, so it's really come just a massively long way in that time span. So as far as modern hardware goes, because that's what we're really more worried about than a history lesson, is it's basically a pyramid, right? At the bottom of the pyramid are what are called end devices or field devices. We have a lot of interchangeable terminology in this discipline. And that is all of your as it kind of the end devices, it's everything that's at the end of the system. So your sensors that are giving you information in, as well as your motors, your pumps, the things that lift the curtains, the things that trigger the fog, your lights, your sound system, the operator panel that they're pushing buttons and hitting e-stops and dispatching vehicles, all of that is end devices giving information or taking information to make the system do what you want it to do. The next level up from that is your IO layer, inputs and outputs. IO, like I said, jargon is very simple in this field. That's what this is. These individual bits here are all IO points, each of these little holes. This is called an IO slice or IO card, IO module, interchangeable. But essentially, these guys, depending on what they're designed to do, each one of these would have a single wire put into it that either an electrical signal comes in or comes out to connect to your end devices and get information from here back to where your software is running. And where your software is running is on this guy here. This is known as a programmable logic controller, PLC for short. Acronyms, we love them. It's basically an industrial computer. It's designed to do its job exceptionally well. Um, the best way I can illustrate it is if you think about the difference between the processor in your desktop computer and the graphics processor in your computer. Your graphics card is designed specifically to do graphics. It does it very, very well, very, very efficiently. That's why everything looks as pretty as it does when you have a super high end, top of the line, brand new graphics card. It's designed to do graphics and only graphics. If you took that processor chip out and put it where your regular processor goes, it would run like crap because it's just not designed to do that job. It's designed to do graphics. Same idea here. This processor, which if you look at it, it's basically a Nintendo Switch. It's a little chunky because of the fan in there, but it's basically a Nintendo Switch in terms of length and width. It's small. It, throw it around. It's heavy, but it's small. It's designed to run logic software super, super efficiently. It will loop thousands of times per second through your software to update the status of these guys, all of your IO, and make decisions and change the status of things according to the physical status of your system. Like I said, thousands of times per second. We have constant supervision of critical situations in an industrial thing, like a bottling plant where you're moving thousands of bottles through an assembly line. You need to constantly know where everything is. If a bottle jams on the conveyor belt, you don't want it to take 5 or 10 seconds before your system knows it and turns off that conveyor. You want it to be instantaneous. That microsecond that bottle gets stuck, the conveyor stops so somebody can go unjam it and then kick it back on again. So it's all about very high speed, very attentive kind of stuff. Now, these guys, this IO, it comes in sort of two designations. You have local IO, which means the IO lives in the same place this does. They are in the same cabinet, like that picture that I showed you. I can show you another picture real quick, like this. This is local IO. All of these blocks with wires coming into them on the picture there, that is local IO. And sometimes, in really big situations, you can't have all of your IO be in the same place as your processor. You have what's called field IO, which is the same stuff. It's just it lives where your field devices live. So, for instance, on Test Track, you have the car go outside and make that big loop around the bank, right? You have safety sensors all over the place out there to make sure that they're keeping track of the cars and where they are and how far apart they are and how fast they're going and all this other kind of stuff. And you don't need this guy out there. You just need to get that information into here to get it back to here so we know what's going on. So this is where field IO comes in because it lives out there on the big bank and keeps track of everything and sends that information back to this guy that lives in the building in a big computer room where there's a whole bunch of these doing their job. Um, and the way that they're interconnected in a modern system is Ethernet. If it's a really long distance, you'll use fiber optic cable because it's able to travel much, much further than an Ethernet cable. But fundamentally, it's Ethernet. It's the same kind of system that you would see in an office building or in your house. It's just industrialized, right? Everything's rugged and industrial. Um, that's this guy here. This is a 4-port unmanaged switch. And it's basically just like a switch that you would see in an office building or in your house. It's just extra tough and extra small and designed to be wired into directly with electricity. Power goes straight into the block here rather than using one of those power bricks into a wall socket. Power straight in, Ethernet ports, done. Um, so we would network. You can see on this guy, there's a couple of Ethernet ports, and that is what connects this whole line of I/O cards, I/O slices, back to a processor here. You can see he's got Ethernet ports up on him too. That's what would connect them together. You would just run a big long Ethernet cable or fiber optic cable over a super long distance to get the two talking to each other. And then I could do an entire video on network topographies, which is basically the layout of networks, because we do safety critical stuff, right? Ride control systems. You can't risk this guy dropping dead and all of a sudden this guy and the processor aren't talking to each other anymore because this went dead. You cannot allow that, right? We have to if this starts screaming, "Oh dear god, stop the ride," and the processor never hears it because this went bad, is a non-starter. So network topology is basically how we lay out the connections between this stuff and this stuff to make sure that we never lose communications between the two ends. Usually there's redundancies. There's either two of these side by side, so if one goes dead, the signal just goes through the other one instead, or you'll interconnect them into like a web. So if part of the web goes dead, instead of it going that way and around, it'll come back this way and go around that way. So there's always at least 2, 3, 4 different ways for information to get from one point to where it has to get to for critical safety reasons. If it's a non-safety critical thing, like a light, we don't jump through necessarily all those hoops because if a light goes out, nobody cares. It's show quality, we care, but it's not going to kill anybody if a light goes out. So, but for ride control systems, absolutely positively, this guy can never lose communication with the core processor without e-stopping everything immediately. Like if this, usually what we do is called a heartbeat. It constantly sends a pulse that just says, "I'm here, I'm on, you can hear me, I'm here, I'm on, you can hear me." And if that heartbeat ever stops, if we ever lose that pulse, basically we treat it like the ride flatlined and e-stop everything immediately to make sure that nothing goes wrong. If this drops dead and we don't know what it's doing, we stop everything and okay, where are we at? Everything stopped, everything's frozen. Go find out why this stopped talking. So we have a lot of safety precautions and a lot of safety systems because ride, but industrial applications have that same kind of safety. If there's any risk to a person, um, if there's a situation where you have like a robotic arm that's moving and doing like auto plants where they're welding the bodies on cars with robots or sparks going everywhere. Generally, those are work cells or work envelopes that are surrounded by infrared laser sensors. So if a person walks up and sticks their hand in the direction of where the robot's doing its thing, that sensor gets triggered and stops everything because there's potentially a person in a place where they might get hurt. So, and that kind of sensor is on its own separate thing where it's guaranteed to never lose contact with the processor that's going to grind everything to a halt because you can't risk people. It's all about safety. 100% of the time, everything is all about doing it as safe as we possibly can do it. Otherwise, we're not fixing a problem, we're just creating more problems. Safety hazards are a huge problem. I hate them. I want to get them out of every system I design to the fullest extent that it is humanly and mechanically possible to do so, because I never want to be responsible for hurting anybody. Um, so that's kind of your, PLC is your brains of the operation, sits at the top of the pyramid. Your end devices sit at the bottom of the pyramid, and these guys fill in the gaps in between. Well, these guys plus these guys together fill in the gaps in between. And then, as far as, uh, yeah, so that's kind of your super brief introduction into controls hardware. I'm going to keep digging deeper and deeper into this topic. We'll get into the nitty gritty engineering in a second or possibly third video, depending on how long these keep going. Hardware and software are both very broad topics. There's a lot to cover there. I could do dozens of videos just on specific bits of hardware. So, I will continue to dig deeper and deeper into this in the next video, and I hope that you learned a little something about controls hardware in this one, at least an introductory pass at it. And we'll see you next time, okay?